In this video, we're going to be talking about a particular method of system identification for second-order systems or systems that behave with second-order dynamics, which is called the decay ratio and logarithmic decrement. I'll say that one more time because it's probably a new word, is logarithmic decrement. Um, So if we're looking at a second order, this is an underdamped system that I've drawn here, and I haven't drawn it too beautifully, but it'll work for our system. The decay ratio is a measure, it's a physical measure of how much the system decays with each period, with each vibration. And so if we have some height here and another height here. We're going to call this line is some y equilibrium, which is not necessarily zero. Then what we can do is we can define the decay ratio, which I'll write as dr, and that's going to equal y of t plus some period minus y equilibrium, and we're going to divide that by y of t minus some equilibrium. And so it's the ratio, what it becomes is the ratio between two amplitudes. So if this is t, this point right here is that same t plus a period. And so y of, here we'll change some colors here. Y of t plus t period is going to be this quantity right here. And y of t is going to be this quantity right here. And so in a decaying system, the decay ratio is always going to be less than 1. And because you have the smaller quantity in blue on the top and the larger quantity in green on the bottom of the fraction. And then we can use this physical quantity to start doing some analysis. And so the logarithmic decrement, so there's a logarithm in there. It's the minus the natural log of the decay ratio. So you take this logarithmic decrement, or you take the decay ratio, you take a logarithm of it, and you're left with logarithmic decrement. And this is useful for system identification. It's useful for identifying some of these parameters of our system. So for example, the logarithmic decrement is equal to 2 pi zeta over the square root of 1 minus zeta squared. It's also equal to zeta times omega n times the period. So we can start to build relationships here. Particularly, if we want to know zeta, we can get it directly from the log decrement with this equation here. So it's the square root of log dec squared all over 4 pi squared plus log dec squared, and this whole quantity is under the square root. So there's a direct relationship between zeta and the logarithmic decrement. And remember, the logarithmic decrement came from the physically measurable decay ratio. So just by taking 2 points on the plot, and you can use any two peaks that are next to each other, exactly one period apart. In an ideal system, that it doesn't matter which two peaks um, to get zeta. And there's a table on page 37 of the book that tabulates the relationship between the decay ratio and zeta. And so once you get zeta, so you're able to measure the period off a system, you're also now able to the um, measure the damping ratio of a system. And with that information, all of the equations and relationships we're starting to learn, you can start to figure out a lot about this system just by these quantities that you can measure.